Okay, so this is an example of what does happen when we want to identify a feature in a signal that's not necessarily obvious in the signal itself, but that's buried in the signal and consists of a time localized discontinuity. So here's our waveform, and what's not obvious is that buried within this waveform is a little step discontinuity that occurs at 1/2 second. And so what we want to do is we want to use the wavelet decomposition and look at the wavelets subbands themselves to see if the discontinuity is obvious. So here's our 3-level decomposition. Here's our original signal, and you can see that as we're decomposing, the low pass output at each level actually changes very little. But if we now look at the high pass output, you can see in this very first decomposition, you do get this clear location of where that step discontinuity occurs. So it becomes very significant, actually in all of the high pass subbands. But if you look at the magnitude, it's a little deceptive because if you look at the magnitude here, magnitude scale in these plots, the largest magnitude clearly is in that first high pass output. So if you were trying to detect discontinuities, this would be a good way to do it because it gives you clear time localization. And of course, if you wanted to eliminate the discontinuity, you could then reconstruct the signal without this particular um, wavelet level. So a good example of this and when this can be a problem is if you're monitoring movement. So if you're looking at 3D motion capture, a lot of times the 3D cameras, they're tracking um, a specific marker. And sometimes the cameras will just lose the marker. Maybe the person turns, maybe something happens, but they literally lose the signal and then they recapture the signal. And because there's no clear XYZ equals 0 calibration, you get this discontinuous jump where the tracking system loses and then regains the marker. When you then are trying to analyze and do something like, what was the joint movement in this particular example, that discontinuity looks like suddenly a person made this very jerky movement when in fact that's not the case. So a wavelet filter could be used to, at the very least, greatly minimize the impact of that step discontinuity and that drop bit that occurs in the measurement system. So an even better way of looking at features is to use what's known as a wavelet packet tree. Um, the wavelet packet tree does continual or additional decomposition on both the low pass and the high pass parts. So it's referred to as a balanced tree. So you're taking the low pass in and decomposing it into low pass and high pass, and you're also taking the high pass in and decomposing it into low pass and high pass. And this is often what's used when you're looking at feature detection and looking for features. The author provides a wavelet packet routine. There is also such a routine available through a nice graphical user interface in MATLAB that will do a wavelet packet analysis. So here's the balanced tree decomposition. So here's an example, okay, of the low pass side and the high pass side. The upper left plot's been low pass filtered 3 times. The upper right's been low pass filtered twice and high pass filtered once. And so you can see what the plots look like. Here's an example of applying this to an EEG signal. And we basically are looking to find 2 features that best differentiate between the 2 signals and plot the values of these 2 features against each other on a 2D plot. So a DB10 element wavelet filter was used. These are two EEG signals taken at different times from the same subject, or sorry, ECG. So here's the data that the author provides. Here is the wavelet decomposition algorithm. And here are the RMS values for the different levels. So you can see that a lot of the levels, the RMS values look fairly similar, but the biggest percent difference is seen in features 3 and 7. So looking at features 3 and 7, if you plot feature 3 versus feature 7, and you plot the location of that point vector for the two different signals, you can see that they appear to be clearly separable. So the interesting thing then comes if you had group 1 and group 2, and you could somehow cluster points around either a group 1 or a group 2 based on these three features. Now, what the author omits here is that this is really not a rigorous statistical analysis. It's just kind of a first order assessment of what might be good features used to classify these two segments of data. So early in the semester, we worked with EEG data. You had a project where you segmented the data into different, you used epochs, and then you segmented the epochs. So this is an example of just a different way to look at that. We used EEG power and RMS values and things like that. In this case, the wavelet is used. The wavelet might be superior because you can see when you do your decomposition, you get some pretty significant differences between the levels where you see a percent difference and the levels where you don't. And particularly if these features have a time localized aspect to them, then you definitely can get better results out of a wavelet analysis than you could out of a frequency analysis. So that concludes what the textbook author provides in terms of wavelet analysis and wavelet decomposition.